Hey, math models. I want to help us along here. I tried making a video this week. It just blew up on me. So I'm going to try again, and I'll go back and cover what I missed for second period. Sorry, guys. We're making a transition. So I want to help with this video to make a transition because let's see. We started the year. Hey, let's start the year with some algebra, some pre-algebra, some memories, dig some things up from the past that'll make us better mathematicians. Then we had a little bit of probability around Christmas, games of chance, statistics. And then suddenly after Christmas, financial math, paychecks, taxes, wages. We went through financial math for a long time, and then we made another shift, to statistics. Math models is like this. We jump around. I hope it keeps interesting for you. And now we find ourselves with geometry. Okay, so I'm just going to briefly cover a couple things that I did the other day. I'm going to take my picture away. Okay, we're going to get into things here in a minute. Taking aside the notes packet we're all working from for a couple weeks, here I have some geometry. Okay, plane M is this piece of green right here. This is plane M. It's a two-dimensional surface. It probably extends further for theoretical purposes, but here it's just like a piece of paper to demonstrate two dimensions. It's got this dimension and that dimension. So the plane is two-dimensional. The line here, I could call this line GH or line HG, because those are the 2 points I have to give me a label. The line has one dimension. It only goes a single direction. I know it's a line in geometry because it has arrows. This indicates that it keeps going in either direction. But something we're going to get into later today is that this is a line segment. This can be measured. There are no arrows to indicate that it goes on forever, infinite distance. So I can measure this one. And if I put that right in the middle, I'd say trying to measure closely. I'll take 51 millimeters. We're about the middle of the dot. About 51 millimeters. Okay, so line segment DE. A line segment is something we can measure that has 51 millimeters for its length. The other features on this plane M, are points A and B and C. Okay, so C is a hole. And I just want to indicate here that geometry can go from 2 dimensions to 3 dimensions. I'm going to use this stick as another line segment, and you could have what they would call an intersection. Okay, so the stick has now intersected the plane at point C. Geometry is taking your math from the past. It's based on some of the math you've done in algebra and other classes, and it's making it three-dimensional. So it's a two-dimensional plane now intersected with a line segment, here represented by a wooden chopstick. And the intersection is at point C. Interesting. Okay, so there is covering this transition to 2- and 3-dimensional math. And I want to make a few points that'll be useful in an exercise where we're going to look at mileages in Texas. So I've told you this is a notes packet from the class geometry, and I'm going to knock out a couple things that'll be covered a little better next year. So follow with me as I mark things out or I talk about them. Here's something that helps with line segments being real measurements. The points on a line can be matched one-to-one with real numbers. The real number that corresponds to a point is the coordinate of the point. So the distance between points A and B, written as AB as a distance, is the absolute value of the difference in the coordinates for A and B. Well, the illustration here is a number line that goes from -4 to +6, and we drew a bunch of these back in the fall studying negative numbers. So if this is in a geometric context, find the length of line segment BE. Okay, so the BE part, that's the address, and this symbol is line segment. That's what the symbol above BE means. Find the length of line segment BE. Well, here I have units of length given to me on this number line. It goes from -1 to 5. And so I think you'll cover other ways next year, but I think the easiest way to do it is to count how many units of length are covered. 1, 2, 3, 4, 5, 6. BE as a length is equal to 6 units of length. Interesting. Down here below, I'm going to try a couple of these, and then I want you to try some. So we'll pause in the classroom. So I'm going to try to find M to N. These are distances. So it doesn't exactly mean negative to the left and positive to the right. Distance is always positive. Distance is always positive. In math, that's the absolute value here that they're giving you, differences between two coordinates. The absolute value of the difference between coordinates A and B. So I'm not worried about negative numbers in this case, because if M is the city Milwaukee and N is New York, well, both are a positive distance. 1, 2, 3. 3 units of length. MN is equal to 3 units. And it works whether I'm going from Milwaukee to New York or New York to Milwaukee. I'm never going negative in that case because I'm building distance either way I go. So you look for the absolute value and you count 1, 2, 3 units. Okay, L to N, K to J, J to L. I'm going to try K to J. 1, 2. KJ is equal to 2 units of length. I'm going to pause here and you guys try 2 and 4 just to make sure we're all doing okay. Okay. In class, I would have gone to the board. Here, I'm just going to put down an answer. L to N, 1, 2, 3, 4, 5, 6. That's a 6. And J to L, 1, 2, 3. All right. I'm going to change my pages. I'm going from page 3 to page 4 for a couple of concepts. Now, ignore it when it says postulates and theorems just now. That's really something for study when you're taking geometry as a course. But here's an idea. Postulate is an idea. If point B is between A and C on a line, then you can use these to kind of add and subtract to find a piece of a length that you don't have. So if A plus, the line segment AB plus the line segment BC, if they add up to the full distance of AC, then you can prove that B is between the two. That seems obvious, like B looks like it's between the two, but we need a little bit of geometry to strengthen our assumptions here. If they're on the same line, you can say that B's in the middle and that this line segment plus this line segment will equal the total, AC. So here are a couple of examples. Find DF, okay, line segment DF. D to E is 23, E to F is 35. I'm going to try adding those. Okay, that's an 8 and a 58. All right, DF is equal to 58 units. It could be miles, it could be inches. I don't know. But they've given me some units here of distance, and so if I want the full distance D to F, I can add those two. Likewise, here I have find GH. Well, FH is 36. FG is 21. Okay, so if I want to find GH, I'm going to subtract. This one was an addition. This one I will subtract 21. And the distance from G to H would be that subtraction, 15 units. Okay, let's ignore 5 and 6 with this picture. But you try 7. I'll pause here for a second. Use the diagram at the left to find the distance K to L. Go. Okay, moving to the bottom. These are some concepts that will hook you up next year for knowledge. Line segments that have the same length are called congruent segments. Congruent. C-O-N-G-R-U-E-N-T. Congruent is like equals. And is used in geometry. Honestly, I'm ignorant whether you guys have used this term in the past, but it's all over the place in geometry. Congruent triangles are the same, have the same dimensions. Congruent cubes is like two pair of dice. They look exactly the same. Congruent line segments have the same length. Here are a couple shown to you, and I know they're congruent now in this picture because they're given this tick mark in the middle. The tick mark, that's what most teachers call it. Like you just reached up there with your pencil or your pen. It means congruent. Okay. If the length AB is congruent to CD, lengths as numbers are equal, and the segments as geometric vocabulary, pieces of geometry, they are congruent. AB is congruent to CD as a line segment. We're doing great. We're about 14 minutes in. This is a practical experience. We're going to skip it because we're doing something practical in class that's maybe a little more real. And I want to cover two more, well, let's call them vocabulary words here. The first one, I hope, you'll see it again today. I hope this midpoint, like middle, like median, these kinds of prefixes mean the middle. So the midpoint of a segment is the point that divides the segment into two congruent segments. This side is congruent to this side. It has the tick marks. If M is the midpoint between A and B, point M, midpoint between point A and point B, so A to M is congruent to M to B. The distance AM is equal to MB. It splits AB in half as a number. The line segment AM is congruent to line segment MB. The midpoint shows you where the middle is. It's not always a point at the middle. Here we have a segment bisector. Okay, so to bisect something, here's a huge hookup for next year. If you if you bisect something, you divide something in half. So here, the segment bisector, it can be all kinds of geometric terms. Could be a point, it could be a line, that's what it is here, line DC, could be a line segment, or it could even be a plane that bisects something, that gives us two congruent line lengths, line segment lengths on either side. Line CD, there should be stronger arrows here. Line CD is a segment bisector of AB, line segment AB. So A to M is once again congruent to MB as line segments, and the measurements are the same. The length of AM is equal to the length of MB. Okay, bottom of the page here. Scratch that out. Scratch that out. That's kind of a fun part. Scratch those two out with some line segments. I'm going to turn over to page 7. Last page. Hold on. Here we go. Given information up top in a geometry equation, it now has some algebra in it. Oof, coming back. It does next year too. Algebra comes back into geometry. Now with this picture and no equal sign yet, we have to figure it out. Point M there is the midpoint of line segment VW. Find the length of VM. Wow. Okay. Photomath usually chokes on these questions because it doesn't know what is being asked. For algebra, we need two things here. Or to solve it, we need to solve for x as a variable because we are given expressions as a representation of a length. So we need to solve for x and then find VM as a segment length. So VM is there. Plug x back in to the expression. I want to show you what I mean here. Okay, the clue is in my geometry knowledge. If this is a midpoint and these two are congruent, I can set these expressions equal, and now I can solve. As long as I have an equal sign and a single variable, why our old friend insolve will handle it for us. Or I could try it by hand. And we did a lot of this in the fall. Okay, I want all my x's on one side. So I'm going to, let's see, this is 3 and this is 4. Well, if I take 3 x's from both sides, these will cancel. And now I have x. I don't want any numbers over here. I want all the numbers on the other side of the equals. So I'm going to add 1 there and add 1 there. It's a statement of equality, so as long as I do something to the left, I can also do it to the right, and these things remain equal, but now I have solved for x. It is equal to 4, 3 plus 1. X is equal to 4. So the length of VM is equal to 4 times 4 minus 1. I took this equation and plugged my x in. 4 times 4 is 16, take away 1. And VM is equal to 15 units of length. Should work the same for MW if these were set equal. 3 times 4 is 12, plus 3 is 15. Perfect. And I know before I even move on, before I even put an answer in a test into DMAC, that I have the correct answer because both plugged in x's come up with the same value for a length in these two segments. All right, scratch this one. Try to answer this one with a star. Answer that question. Maybe we need more lines so you don't answer that one by accident. Answer A, B, this one. Identify the segment bisector of AB. Then find AB. So there's numbers on each of these, and I want to know what is the segment bisector. Here's a clue on the second one. The bisector is here, whatever this is. I have 2 congruent marks there. Okay, so this happens to be a ray, if we didn't cover it very well the other day. Starts at an endpoint, goes through another letter, continues on with an arrow. So the bisector is ray MC. So it's symbolized with the 2 letters and an arrow over top. I want you to attempt all 3 of those. There's that one. And then I want you to attempt all 3 of these. And when we finish, we will move on. First we'll take a break, and then we'll move on to a different subject. I'm going to try this. Okay, identify the segment bisector of E to F. So bisector here is point M. Okay, I could also say point M. And find E to F. Okay, the full length. 3x minus 4 is equal, because of the bisector, to 5x minus 12. Let's add 12 here. This will make this positive. Negative 4 plus 12 is positive 8, and these cancel. I'm going to take 3 x's from here. That'll cancel. Minus 3x here. 2 x's. So 2 times what number gives me 8? Well, 4 is equal to x. That's not the final answer, though. They want to know what the entire length of EF is. So E to F. I'm going to try plugging it in. 3 times 4 minus 4. 5 times 4 minus 12. 3 times 4 is 12. Take away 4, that's 8. 5 times 4 is 20. Take away 12. Good, we did our math right. Also 8. So the total distance from E to F is 16 units. Mr. Akak and I will move around the room and see if we can help you try these. We've got to brush up on some algebra skills and some new concepts in geometry. Okay. And then once we finish this, which is 1, 2, 3, 4, 5, 6, 7 problems, 2 that are done for you, 5 problems total, we will move on to an activity. Thanks for your attention, guys. I'll talk to you later. Hope you all at home are doing well.